Hello, my name is Rodrigo Galeano. These are my lectures in transfer phenomena. In the first lecture, I'm going to talk about conservation equations. These are the building blocks to solve any type of problem in transfer phenomena. This is why I want to talk about these in the first lecture. Now, what are transfer phenomena? They are the study of flow. We can have flow of fluids, for example, moving water. We can think about flow of heat when we heat a teapot, for example, or we can have flow of mass when we have a dye that is diffusing or spreading away within a liquid medium. So even though these three processes are very different, they are all studied by transfer phenomena. Now, the first tool that we have to to solve problem structure phenomena is the concept of conservation. Okay, this is the most important concept in transfer phenomena. And this says that certain physical quantities are conserved. For example, momentum, which is related to the fluid of a liquid, energy, which is related to heat transfer, and matter, which is related to mass transfer. And we use the conservation principle in order to write down conservation equations and solve the problem in transfer phenomena. Now, the first type of conservation equation that we can write is the integral form. Think about a volume V that has a surface S. This surface S is orientable. That means we can define a normal vector n pointing outwards. And within the volume, we have a certain concentration V of a quantity that is being conserved. For example, mass, energy, or momentum. Now, throughout this volume, we have a vector field F that transports V. So we have V, which is the concentration as units of a certain quantity per unit volume. We have F, which is the vector field that transports V, so it has units of quantity per unit area, time. And we have BV, which is the generation term. So it has units of a certain quantity per unit volume, time. So whatever thing is generated, we measure that with BV. Okay. So what we can write is the following. The total amount of B that we have within our volume is B, which is a concentration integrated over the whole volume. Now, to know the rate of change of this, we write d dt. Now, this rate of change is given by the flow outwards of our volume. The normal component of the flow is F dot n. And if we integrate this over the whole surface, we have the total flow outwards. Now, because in the left-hand side, we have the total increase in B, we have to put a negative sign here, because that gives us the total flow inwards. Now, we have to take into account the generation term, which is given by the integral of BV over the whole volume. Now, this is the rate of change, total rate of change. This is including the negative sign, the net flow inwards, and this is the total generation term. And this is known as integral form of conservation. This is also known as weak form because it tells us the conservation principle in a certain average or aggregate way. Now, if we have, for example, a positive net flow inwards, that means we have more and more fluid within our volume, so the change should be positive. The total amount of quantity B that we have increases with time. Also, if we have, for example, a chemical reaction that is producing a certain species, then this term is positive, the integral of BB, and that makes the rate of change of B within our volume to also be positive. That's what the integral form of conservation says. Now, there is another way in which we can write this integral form, which is stronger, and it is called the differential form of conservation. So let me write first what we had before. The integral form was d dt of the integral of v over the volume. Let me write this in the left hand side, the surface integral plus f dot n integrated over the surface, okay? minus the integral over b of the generation term. This is what we had before. Now I want to use a theorem in vectorial calculus, which is the divergence theorem. This allows to write a surface integral as a volume integral. So this is that f dot n ds can be written as an integral over a volume of a specific differential operator that acts on the vector field, which is called the divergence operator. The divergence of f is just the partial derivatives of f with respect to each component, dx, dy, and dz. Okay, so this allows to write this integral in a different form. So let me write the conservation equation in the integral form of conservation equation in the following form. I'm going to introduce this derivative also inside the integral because the volume v, I can say that it is fixed. I can just introduce this derivative as a partial derivative with respect to time of b. Then the surface integral I will write as just the differential operator acting on f, and then I have the generation term. So this is going to be my integrand of the volume integral. This is equal to 0. Now, because this can be true for any volume independently of its size, this means that what we have here should be always equal to 0. And by doing this, we obtain the differential form of conservation, which is dB dt plus the divergence of the vector field minus the generation term equal to 0. Now, this equation means the following. If we have a vector field that has positive divergence, okay, positive divergence, that means if we analyze a volume of space, the vector fields are going out of that space, then the equation says that the derivative of b with respect to time should be less than 0, which makes sense. If the fluid is going away, it's going out, we have less and less fluid inside a volume, so concentration should decrease. Now, if the vector field is such that it has negative divergence, then that means if we analyze the surrounding of a point, that point acts as a sink, okay? All the vector fields are converging to that point, and then the equation says that the concentration should increase with respect to time, which makes sense because we have more and more fluid, more and more energy, more and more mass, so concentration should increase with respect to time. Also, if the generation term is positive, then that means also that dB dt should be also positive. We are creating mass or heat, and then the concentration should increase. Now, this equation is also called strong form because it states the conservation equation in a very rigorous and restrictive form. Okay. Now, we have the two differential equations, the two ways to write down the principle of conservation, which is the differential and the integral form. And I like to compare these two by specifying the temperature, for example, in a volume. The differential equation says if the temperature is, let's say, 40 degrees C, then that means that at every point that we see in our domain, then the temperature should be also 40 degrees. It should be 40 degrees. At any other point, it should be 40 degrees. Now, the integral form of conservation tells us just the average temperature. If I say that the average temperature in a volume is 40, then that means that at this point it may be 41. At this point, it may be 40. At this other point, maybe 39. But when you average all the temperatures out, you obtain 40 degrees. So that's what the integral form of conservation says. So as we can see, the differential form is way stronger. It's more rigorous. And a solution of the differential form is necessarily a solution of the integral form of conservation. But a solution of the integral form doesn't really need to be a solution of the differential form. But we use both equations to solve problems. One may be more convenient than the other depending on the problem. Now we can see some examples. We can have fluid flow. To analyze fluid flow, B is the density, okay? It has units of mass per unit volume. Then F, the vector field that transports the mass, is always a concentration, which is rho times a velocity, okay? and it has units of mass per unit area, time. And then because mass cannot be created nor destroyed, dV equal to 0. Okay? And the differential equation is v rho dt plus the divergence of rho v equals to 0. This is a very famous equation known as continuity equation. Now, to analyze what the continuity equation says, I would like to write this in a more specific form. So I can write v rho dt, and I will use an identity of vector calculus to write v dot grad. So I'm decomposing this term here. V dot grad rho plus rho divergence of V. This is just an identity. Now, this type of expression has a different name, which is known as material derivative. And it is written as big D, capital D, d rho dt. And the idea behind material is because we follow a material point. That means if we follow the particle, we see the changes in density with respect to time. And this is equal according to the equation. Let me write that in the right hand side, minus rho divergence of the velocity field. Now let me write rho in the other side. So we have 1 over rho, the rho dt. So this is a change in density with respect to time per unit density, or unitary change in density. So as we move along the frame of reference of the particle, what we see is that the change of density per unit density with respect to time is given by the divergence of the vector field. Okay, so that means if the vector field is such that it has positive divergence, then the lines of velocity are diverging out of the region. We have less and less fluid, and the density should decrease with respect to time. That's what the equation says. Also, if the divergence is negative, that means the fluid is converging to that point. Okay, we have more and more fluid with time. That means that the density should increase with time. That's what the equation says. Now we can have an example or also in heat conduction. In heat conduction, B is the total energy of the system, which is given by the enthalpy. The enthalpy has units of energy per unit volume. Then we have the vector field that transports the enthalpy is given by minus the conductivity times the gradient of temperature. This is known as Fourier's law. And it has units of energy per unit area time. And then we can say there's no generation of heat. We don't have a chemical reaction that is exothermic. We don't have a resistance that creates heat. So BV equals 0. And the equation is dH dt plus the divergence of minus K grad T equal to 0. Now we know that a differential change in enthalpy can be written as rho, heat capacity, times a differential change in temperature. And I'm going to use also a vectorial identity in vectorial calculus, which is the divergence of the gradient equals the Laplacian. So we can write rho Cp dt dt minus, I'm going to say that the conductivity is also a constant, K Laplacian of T equals 0, which can be written as the derivative of temperature with respect to time equals alpha times Laplacian of T. Well, alpha is K over rho Cp, which is the thermal diffusivity. Alpha measures how much the heat diffuses in a medium. And this is a balance between the conductivity of the medium and its heat capacity. Okay, I'm not going to go into the details of this diffusion equation because I'm going to do that in the next lecture, lecture number 2. Now, the final example that we can see here is mass diffusion. When we have mass transport, B equals the concentration, which has units of moles per unit volume. F, the vector field, is really similar to Fourier's law. Is minus D, which is the diffusivity coefficient, times the gradient of concentration. And this has units of mole per unit area time. And this is known as Fick's law. Very similar to Fourier's law. Now, because there's no chemical reaction that generates a chemical species, BV equals 0. So the differential equation is dC dt plus the divergence of minus d grad C equals to 0, which is dC dt. Let me write that down on the right hand side. Diffusivity coefficient times Laplacian of the concentration. So the diffusion of mass has the same form, the equation has the same form as the diffusion of heat. Again, not going to explain this equation because I'm going to do that in lecture number 2. Okay, now we have the differential equations, and to solve them uniquely, we need some boundary conditions. To obtain the boundary conditions, we need to do a balance in or at the interface. Okay, an interface separates our domain that we are studying with the other domain. So it separates a region 1, where we have the concentration profile and the vector fields, with a different region that I call it 2. And the interface is orientable. We can define a normal vector to the interface. In region 1, we have a concentration profile and a vector field. And in region 2, we have a different concentration profile, let's call it V2, and a different vector field, F2. Okay, so imagine we have some vector field that gets to the surface from one side and a different vector field that gets out of the interface. The interface is important because it allows for discontinuities in the concentration profile and in the vector field. And we have also a generation term that is in the surface what is being generated. So if we have a surface where Bs is positive, then that means we have a small vector field here and a really big vector field here, because all the things that are generated, whether it's heat or mass, are going out of the surface. If Bs equals to 0, then that means we should have continuity of the vector field in both sides of the interface. And if Bs is negative, that means we have a big vector field coming here and a small vector field going out, because the thing that is conserved is being destroyed. Okay. Now the conservation is stated as follows. We have this normal component of the vector field 2, okay, minus the normal component of the vector field 1. So this is whatever gets to the interface, the difference between what we have in region 1 and region 2 should be equal to whatever thing it is created. Okay. If Bs equals to 0, there's no generation, then the normal component of the vector field in both regions should be the exact same thing. Okay. Now the boundary condition comes when we define one component. If we say, for example, that F1 is a constant, we give it a specific value. This is known as Neumann boundary condition. Okay. If we specify the concentration, for example, B1 equals to B0, this is known as Dirichlet boundary condition. Okay. Now there's another case in which the interface has a velocity. So it has a velocity, a normal velocity in the direction of the normal vector. Okay. And this again separates region 1 and region 2. In the previous case, the velocity was 0. The velocity of the interface is 0. And we have to change a little bit the balance equation when we have this, because the motion of the interface create what is called fictitious fluxes. So we have to do the balance in the frame of reference of the interface. So the moving interface doesn't see just F2, but rather it sees F2 minus a fictitious flow that is given by a concentration times a velocity. Okay? And this, I take the normal component again, just like before, and then I subtract F1. But the interface doesn't see just f1, but rather it sees the difference between f1 and b1 times the velocity of the interface. Okay, I take this normal component, and this should be equal to the generation term. And this equation we can use to calculate the velocity of the interface, or at least the norm of the velocity of the interface, which is given by f2 minus f1 dotted with the normal component, normal vector, minus bs divided by b2 minus b1. And this is important whenever we have change of state of the matter. For example, when we have from solid to liquid or liquid to gas or any other change. Whenever we have a moving boundary, this equation is important. Okay. Now, in the next lecture, I'm going to talk about the fundamental solution of the diffusion equation, how interpret this solution, and what means each term in this. So, see you in the next lecture. Thank you.